Jeff, it's all you.
Just a brief discussion of orbital dynamics on the way to the moon. We heard about launches. We're going to hear about landing systems. The initial landing systems that we're dealing with, of course, are for CLPS, for unmanned payloads. I want to look ahead also into orbital requirements when you have a human mission. So first of all, let me share my screen here. Right. So you all know what this is. It's our moon, and it's so we have the equatorial regions and the polar regions, and of course we're very interested in accessing the South Pole. Why did the Apollo missions and all the early lunar missions go to the equator? Well, hopefully, at least some of you have had some orbital mechanics in your background. You know that the moon's orbit is inclined by about 5 degrees to the ecliptic plane. So, and of course, the Earth's equator is inclined by 23 degrees. So the basic point in celestial and orbital mechanics is to change planes is generally a very expensive maneuver because, when you're moving at, for instance, Earth orbital velocity, which is about, 18,000 miles an hour, if you do a vector diagram, so you have, let me annotate here. So yeah, you're moving. I should make that an arrow actually. So yeah, you're moving at 18,000 miles an hour, and you want to change the inclination of your plane. This is the resulting delta V that you have to do, and you can see that if this is 18,000 miles an hour, and you want any sort of a reasonable change, this number, this delta V that you have to apply is going to be rather large. And so it's frankly much easier from an energy point of view to go to the equatorial regions because that's closer to the ecliptic and equatorial planes of the Earth, which is what we launch out of. When we launch from Cape Canaveral, you're into a 28-degree orbit. So nowadays, of course, we want to. Oh, and the other thing is, for the Apollo missions, then of course they were moving around. They had the service module, which was waiting there to take the crew back, continued to go around in equatorial orbit. So it was basically flying over the landing site pretty much every orbit, so every 90 minutes, which meant that pretty much any time the crew on the ground wanted to leave, if there was an emergency and they had to leave early, they could leave and do a rendezvous with the service module. What happens when we go to the South Pole? Well, in that case, first of all, we're assuming that we have the rockets big enough to give that little extra plane change to get out of the Earth's ecliptic plane and basically get above the moon's orbit so that you can go into a polar orbit. Now, if you're in a low altitude polar orbit going around the moon, you're flying every orbit, you're flying over the North Pole and the South Pole. And so once again, if you need to get back in a hurry, and this has to do with certainly for the constellation program, I don't know how they're working it for Artemis, but for back in the constellation days, there was a requirement for anytime return to Earth. How long would you have to wait if you had to get back in a hurry? Well, if you're right at the South Pole, as I say, that's not a problem because the orbiting spacecraft doesn't matter whether it's in a low lunar orbit or a highly elliptical orbit, it's always going to fly over the South Pole and the North Pole. And so you can basically rendezvous with that at any time. That's one of the advantages of being right at the pole. The more complicated situation occurs if you are anywhere between the equator and the poles. So if you're at a mid-latitude here, now imagine that you're in a either a polar orbit or a slightly inclined orbit. But remember, the moon's um, uh, near side is always facing the Earth. So the moon is rotating once every month. Um, Roughly speaking, whatever orbit you're in stays fixed in inertial space. There are there's precession and the like. That's a second order effect. Let's just imagine that the orbit is fixed in inertial space, and so basically, as the moon rotates with respect, because the moon is not fixed in inertial space, as I said, it's rotating once a month. And so it's rotating. You can look at the moon rotating under the inertially fixed orbit, or you can look at the orbit rotating around the moon. But basically, it's only going to pass over this mid-latitude site every other week. So twice per month, once on the ascending and once on the descending pass. And so that makes things much more difficult. And that's the reason why if you have this was the situation for a low energy orbit, and the orbital velocity around the moon is, I think it's a little under 2 kilometers a second. So if you wanted to change that plane so that you had to get the people back in a hurry, that becomes very expensive because, again, the basic velocity that you're starting out with is large. And that's the advantage of what we've heard about these highly elliptical orbit, whether it's a near rectilinear halo orbit or just any sort of a high inclination orbit. So imagine that you're in a polar orbit, but that when you go over the North Pole, you go really far away from the moon. That means at the apogee, of course, your velocity is at a minimum. And if the orbit is elliptical enough, then your apogee velocity, which is this number here, is small enough so that the actual delta V requirement to change your plane becomes manageable. And so basically that's what I wanted to leave you with, was why we would favor these highly elliptical orbits, if you are not exactly at the South Pole, but you're somewhere, in intermediate latitudes, because then if the crew has to come back in a hurry, if you're in a 1 day orbit, for instance, highly elliptical, I think that's about 15,000 kilometers. I don't remember exactly, but in any case, what it means is that within 1 day, you can, when you get up to apogee, you can change your plane so that the next time you come around the orbit, you'll fly over the landing site and the crew can basically do a rendezvous with their ride home without any further plane changes being required for the orbiter. Then, of course, you'll have to do your plane change to get back to the Earth, but that's always a requirement if you're going into a non-equatorial orbit around the moon. So that was just very briefly a discussion of some of the requirements that we put on lunar orbits. If you're just sending a CLIPS payload and there's no requirement to get it back, then of course you don't really care about this anytime return. The only thing you have to worry about is the initial plane change to get into a polar orbit or any other non-equatorial orbit. So for those of you who have had orbital mechanics, this is pretty simple stuff. If you haven't and have any further questions, happy to answer it, or talk to some of your orbital mechanic smart friends, and they can fill you in on some of this. So that's it. And I think we wanted to get started with some of our speakers at about 9:45. So I've gotten finished at the right time.